Hello again, everyone. Good day, good morning, good afternoon, good evening, good night, wherever you are in the world, and welcome to Freaky Physics again. Today, we don't have a lesson, we just have a live stream. So, we'll stream for about an hour today. Reason being, some of my students have requested for me to discuss a particular topic, specifically, how to answer paper 3 questions in the IB exam. Okay, what we'll do today is I will not be answering an actual past paper question or, get something from the past papers, but instead we're going to go through the main ideas again of how to properly interpret data. Okay, the reason why I want to go through this, aside from this being a requested topic, is because for those of you who are not yet taking the exam, basically this is a good opportunity for you to learn how to properly handle data, specifically in the IB and also quite possibly for the A level exams for physics. Okay, so uh, so what we'll do today is I'm not gonna look at any source as well, but we're gonna go through some key ideas first. Once we go through those key ideas, we're gonna go through how to properly apply them in certain problems. Okay, so um all right, so with that now, let's just get started. So let's go to the board. There we go. Okay. So first of all, when you're doing an experiment, let's start with that idea first. Whenever you're doing an experiment, burst sorry, the first thing you're gonna do is gather data. And when you gather data, so in the experiment, okay, this is not designing the actual investigation, but this is the actual data gathering step. Okay, so this is the data gathering and analysis and analysis. Okay, now we will go through how to do this properly. First of all, again, we're not even gonna start from the procedure. We're gonna start with actual data presented. Okay, so let's of course, in order for us to further understand this, let's give an actual example. Let's say let's say for instance that you have an experiment about let me think of one real quick. Okay, so you're basically having an experiment about um the frequency of vibration. So let's put this here, the frequency of vibration, um and vibration, and how it affects, for instance, the final temperature. Okay, I think final temperature after 5 minutes of vibration. Okay, now before we continue, you will see that um the way I presented this question, this is not actually still complete. The reason being, I didn't say here what's vibrating. You must state everything you can specify in the experiment. So in this case, let's say that this is the frequency of vibration of water placed above a 5 cm speaker. Okay, so of course, in this particular case, again, you've never probably encountered this kind of experiment, IB, A level, major physics, whatever. You've probably not encountered this, but that's not the point. And if you think about this further, you have not learned of any equation that would relate the frequency of vibration to the final temperature. Again, that's not the point of paper 3 for IB, or for that matter, which paper was this for A level? Uh, I think this is either paper. I think this would be paper 4 in A level. Okay. So the idea here is, okay, I'm just gonna further draw this so you understand what's happening. But again, in terms of answering the question, this doesn't matter. Okay. But let's set it up either way for us to understand the whole setup. So in this case, you have a beaker full of water, and then you're gonna suspend it a little bit above the speaker like this, and then this speaker will vibrate at some frequency. Okay, and you're gonna see what its final temperature is at the end. Okay, now, okay, paper 3 for IB and paper 4 for A level, they may ask slightly different questions, but the key ideas that they're testing is the same. They are testing mostly three things. Okay, so for A level, I'm gonna focus more on IB because that's what we're doing. But remember, this is also true for A level paper 4. Okay, so what are the main things that they would be testing here? The first thing is how you the first thing that they would test is unit conversion, or what's the other what's the other thing here? It's either unit conversion or uh homogeneous, let's just say it like that, homogeneous units. Okay, in other words, your units, they are consistent with each other. Now the second thing they would normally test is reading and converting graphs. Now in A level, I don't really see the conversion of graphs, but they do reading of graphs. Okay. Okay, conversion of graphs. And then the third thing that they normally ask for is um, uncertainties. Okay, so let's start with the first question, with the first part, a unit conversion type problem. Okay, now let's say I'm going to assume, I don't know the actual equation if there is one, just so we're clear. So I'm going to put a disclaimer here before we do anything here. Disclaimer. Okay. All equations in this example are probably wrong, but we'll use those equations to really push the point across. Okay. All equations in this example are probably inaccurate. Okay. Inaccurate. Okay. So that's the disclaimer. But again, the important thing here is that accurate or not, the point is we're going to check whether everything matches. Okay. So let's go straight to the first part, unit conversion. Okay. Or rather, let's not use the unit conversion. I think you can all convert units pretty easily. So we'll go straight to the second bit on that unit or homogeneous units. Okay. Now, whenever you need to see homogeneous units, all you have to remember here is that the units on one side of the equation must somehow cancel out with other units on the other side of the equation. In other words, they must have the same units. Okay, so here's the example now. So let's say here a student, um, let's see, a student hypothesizes that um, T temperature varies with F using with the following relationship. Okay, so let's say that the temperature squared is equal to the frequency cubed times some constant k uh, plus T0, where T0 is the initial temperature. Okay, so again, let's hypothesize this temperature. Let's hypothesize this for now, and let's assume that this is correct. Let's assume that this is correct. So, excuse me. Let's use a highlighter here real quick. So that's our equation here. All right. So with this in mind, normal question that you would see, again, this is either A level or IB. A normal question here that you would see with this particular setup now is this. Okay. Find the units of K. Okay, so that's the first question. Okay. So of course, oops, sorry, I forgot something. This should be squared here. I'm going to put squared here. Okay. Now, we'll get to why I changed that to squared later on, because that's also another skill that you need to show in the exam. But going back to this first question, find the units for K. Now, the key idea when you have homogeneity or when you're testing for homogeneity is, again, all units must be the same. So all units must be the same. Yeah. So this is the key idea. Now, specifically, we're gonna make this a bit more specific. All terms in the equation must be in the same unit, but each quantity, so in this case the k and the f, or and the t and the t0, each quantity can have different units. Okay, so that's the first part. So the second thing that must come here now is, this also means that any two terms or more, okay, I'm sorry, not terms, any two quantities put together in one term, in a single term, must um, have some of their units cancel out. Okay, units cancel out. Now, this is what I mean. Let's go back before we go to that question of find the units for K. I'll give an example here on the side. So for example, we know for a fact that F equals MA, right? And we also know that F is equal to the change in the momentum over change in the time. Now, what we're not gonna focus on this. Okay, what we're gonna focus on in this particular example is this part. Okay, so how can we know that they have the same units? So what we'll do now is we'll put the units for mass. This is kilogram. Okay, now A is acceleration. That's gonna be meters per second, and I'm gonna write it like that. Okay, now the other one, oh sorry, per second squared. Mistake there. Okay, now on the other side of the equation we have change in momentum. So basically it's just the momentum, and we know that momentum is kilogram meter per second. This is kilogram meter per second, and I'm going to do that, and then I'm going to divide that by second, which gives us kilogram meter per second squared on the left side, and the same thing, kilogram meter per second squared on the right side. Homogeneous units, it works. If the units don't cancel out like this, or they're not identical like this, then something's wrong with the equation. Okay. So going back to our example. So, and I'll zoom in a bit, zoom out a bit here. So find the units of k. Let's go to that now. So the idea here is we're gonna copy it here first so we can manipulate this more easily. Kf cubed plus t0 squared. Now earlier I didn't have that squared. Now I immediately corrected myself, right? The reason being, look here. If let's keep the t0 for now. This is in kelvins. So that's going to be square kelvins, right? So this means this must also be in square kelvins. And this must also be in square kelvins. Must, right? But here, if you leave it at t0, you don't have that squared. So you can see here that the k squared and this k, they cannot do anything about it. They cannot cancel out. So basically, that's why our initial equation was wrong. So that's why I had to do that correction for t0 and put that squared there. Okay, so we know, okay, so this is the first step. You know that the units are like that. Now we're going to focus here. Okay, I'm going to make that capital K to make it more clear. Okay, so if we focus on that, I'm going to use blue now. Okay, if we focus on here, the unit of K, F cubed, is in Kelvin, right? But the thing is, frequency is hertz, and hertz is 1 per second. So this is going to be K over second. Oh, let's write it with scientific notation. That's going to be small k times second cube per second cube should be equal to Kelvin, right? The unit must be that. So in other words, you know what? I think I may have misused a letter. I think I'll just change the letter from K to C, so to prevent confusion. Okay, so let's change that to C. All right, and this is C, right? So going back, so C will have the units Kelvin second cubed. So that's our answer. Those will be the units for C. Okay. All right. So again, that's the first part. Homogeneity. You always make sure your units are consistent with each other. And then you use that consistency to find the units of some unknown constant like this. Again, this particular skill is done in both A level and IB. And in fact, I'm pretty sure this is done for all other qualifications. You must be able to do this. Okay, so that's the first one. And again, this is a really common problem for whatever qualification. Okay. Uh, okay, so that's the first part. Now let's go to the second part. This time, I'm going to hold on. Let me just zoom out here first and there and do this. Okay, so let's go to the second bit and let's go straight to the question there. The second bit is reading and conversion of graphs. Now, in fact, I think I want to do this last. Okay, let's go to the second one here, uncertainties. Now, uncertainties can either be given to you or could be found from the graph, right? So, let's put that here. Uncertainties. Now, I know for a fact that this is usually taught at the beginning of any physics course. Okay, so uncertainties. Okay, now remember, I just want to make sure that you all are aware of this. So when we look at uncertainties, we usually think about it in from either the source or the type, right? Now, the source of the uncertainty can be either the instrument, okay, or the variation from a mean, variation of values from mean, right? Or from the average. Now, I'm kind of using a technical term here on variation of values from the average, but all you have to remember here, at least for the lower levels, is that when we say variation, it's just how far off a particular value is from the mean. Okay. Now, whenever you're doing this, if you're looking at it from the instrument, remember, you either look at the instrument if it's an analog or a digital device. Now, when you have an analog device, the uncertainty, and I'm going to say delta x here, will be equal to half of the least count. This is the technical term. The least count is basically the smallest possible measurement you can do on that instrument. On a digital instrument, the uncertainty will be equal to the least count. Okay, again. So analog, the uncertainty is half of the least count, and in digital, it's the least count. All right. Now, whenever the second part is variation of values from the average. What do we mean by that? So, for example, you have some values. I'll give you an example straight away here. So, let's say that you have 1, 1, 1, 2, 1, 1, and 1. 1, 2, 3, 4, 5, 6, 7, 8. Okay, let's do it like that. And then let's put another 2 here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, there are two ways to do this variation. Now, the one that you would normally expect to see at high school levels, like again, A level or IB, is that if you have these, the first step is to find the average. Okay, so in this case, that's going to be the average will be 2 plus 1 plus 1 plus 1 plus 2 plus 1 plus 1 plus 1 plus 1. You know what? I'll turn on my calculator because I am feeling a bit lazy with this. I don't want to think in my head. So I'll do 2 plus 1 plus 1 plus 1 plus 2 plus 4 1. So I'll just put 4 there. And I'm going to divide that by how many values? 1, 2, 3, 4, 5, 6, 7, 8, 9. So 11 divided by 9 on the calculator divided by 9 will give you 1.22. So your average value equals 1.2. In fact, let's make this even more accurate. I'm going to put 0.0 here just to give it 2 sig figs. Okay, 0.0, 0.0, 0.0, 0.0. Okay, so the average is 1.2. And then, okay, there are two ways to find the uncertainty here. So 2 is uncertainty, right? The the easier one and the more accurate version. The easier one here is to use the half range. And this is going to be your maximum minus minimum value divided by 2. And that's your delta x. Okay. Now the other one, and it's a better way, but for most part, we don't do this because, like I said, the half range technique's the easier one to do. The uncertainty here could be the maximum difference from mean, okay? From the mean or from the average. So in other words, this is going to be 2.0 minus 1.2, okay? 2.0 minus 1.2, that's going to give us 0.8. And then the other one is 1 minus 1.2. Let's do it the other way around. 1.2 minus 1, that's going to give us 0.2. And then choose the bigger one. Choose bigger value. So 0.8, right? So this means in this particular case that delta x should be equal to 0.8. Which technique is correct? The more correct technique is the second one, but the easier technique is the first one. Which one would you prefer to do in the exam? The second one is acceptable, you can use that. Sorry, the first one is acceptable, you can use that. Again, make your life make it easier for yourself. Now, another thing you can do here is another reason why this is easier, the half range is easier, is because on the second technique, if you're really gonna do this on an actual paper, this is gonna take you time because let's say that I didn't give you easy values. What if this was 2.1, 1.0, 1.1, so on, so on, so on, right? you're still going to have to find the minimum and the maximum values, but you're going to have to find the average anyway, right? And then you're going to do an extra calculation. This basically takes you one calculation. You just take the maximum minimum divide by 2. But this involves a third number and you're doing the calculation twice, making it longer and therefore not the viable option for an exam. We're talking exams here, people. Okay. What do we mean by that? If you were actually doing this for a paper, for a research paper, this would be the better technique. Now, having said that, later on, when you're done with these exams, you're going to go to university, you're going to go to colleges, whatever, right? This technique, both of these techniques are not good enough for college later on. I'm telling you that. So basically, what am I telling you? In terms of the exam, do this one, the half range. It's going to be way easier for you, and you're going to be wrong anyway if you do it in college. So just do this. Okay. Whatever they do in college, I will either teach you that later or you let your professors teach you that later. But for now, yes, just use half range. Okay. So in other words, our uncertainty in this case is not going to be 0.8. So our final answer here would be, no, let's not do that there. Okay. So our final answer here for the reading would be 1.2 plus or minus 0.5. So in this case, let's just write that here. This is going to be 2 minus 1 over 2. 2.0 minus 1.0 over 2. That's going to give us 0.50. Okay, or 0.5. So our uncertainty or our value here will be 1.2 plus or minus 0.5. Again, personally, I don't like this method personally because it's not actually a good value. But in terms of the exam, this is the fastest way to do it. Do it this way. Okay. Again, doesn't matter what exam it is. IB, A level, I don't know what else. Those are the ones that are really familiar to me, right? So hopefully that's clear. Yeah. So whenever you're given this, you're gonna have to do that. Now let's go back here to this part where we said there when we say uncertainties, we either you look at the source or we look at the type. Now in type, we're gonna do it like this. Okay, so for type, you can have either random or systematic. Okay, systematic. Now, whenever you have a graph, okay, let's do a linear graph. So for example, you have some sort of linear graph like that. Okay, now the random error, and let's put some points around our graph like this. Okay, and we'll label this point here, the y. That's gonna be the y-intercept. Let's just call it y-intercept. Okay, now systematic. Okay, now the random error is basically this, how far your points are from the average. How far points are for average, from average. Okay, again, your random error, random uncertainty, it's properly called error. Okay, is again how far your points are from your average. In other words, it's this distance to that point, it's this distance to that point, it's that distance to that point. Okay, so of course you've learned this several times before, but I want to just emphasize this again. How do you reduce this? Reduced by uh this is going to be reduced by increasing your number of trials. Increasing trials. Okay? Because if you have a lot of trials, then you're going to get closer and closer to the true average, and therefore you're going to get more closer and closer to the actual value. Okay? Now, the systematic error is due to instrumental or measurement technique failures. Instrumental or procedural, I'll just say it like that, procedural errors. Okay, for example, you happen to have a ruler that was faulty, that is faulty. It's let's say that its measurement of 1 centimeter is actually 0.95 centimeters. It's short by 5 millimeters, but that will add up. That's instrumental. Okay. Now another thing, procedural could be like you're consistently measuring the length by putting the end of the ruler on the end of the object, when in fact you should be putting the zero mark on the end of the object. But you're unable to because of limitations. Like for example, you're measuring the length of or the width of your table, but there's a wall in the way, right? So procedural. Now, if you have a procedural error, this will leave you a y-intercept. Okay, and that y-intercept is going to be your systematic error due to procedure. In other words, in other words, you can reduce systematic error by proper analysis of your data. So again, I'll use blue here now. So systematic error is reduced or eliminated eliminated via proper data analysis. Okay. Okay. So okay, that's in terms of doing the experiment. But how about in terms of the paper that's gonna do this? So paper 3 again for IB or paper 4 for A level. Um so that's all well and good to know. How will you use it? Now, in order for us to do this, to show you properly how to properly account for this, all we have to do now is actually take a look at some graphs, which now goes to the last bit of reading and converting graphs. Okay, so the example here is going to be something like this. Okay, so again, same disclaimer as before. The example will probably be a wrong equation in reality, but that's not the point. The point here will be how to properly do the graph. Okay, so let's say you're about to not about to, let's say that you're given your graph. uh you know what, let's put a table in first. So let's go back to that old equation. Remember our equation was t squared or was it t squared or t cubed? T squared, right? So our graph was t squared is equal to some value of k f cubed plus t 0 squared. T0 squared. Okay, so how will let's put okay, so how do we know that this is the particular thing, that particular example? Now I'm just gonna put some random values for t, and I'm gonna try to put this in spreadsheet. So let me open up a spreadsheet here, and I'm going to just create some dummy data, fake data. Okay, so I'm just gonna do what just happened to my spreadsheet. That's weird. Okay, uh, let's do that again. All right. Uh, okay, I just got a notification. Hold on, sorry about that. While I'm waiting for my spreadsheet to open. Okay. Oh, it's updating. Okay, I'll just never mind, it opened right there. Okay. Let's do that again. I'm just gonna make the um okay, let me think about this. I'm gonna start with 20, 25. No, no. Let's start with 30. Let's start with F. Okay. All right. I think I got how to do this. All right. Give me a moment to make the fake data and make it look believable. Okay. So in this case, okay. And let's start with 100. Yeah. Let's start with 100, 150, 200, 250, 300, 350, and 400. Okay. So T. Okay, I'll just put something here first. T0. Let's put that. Okay, and then uh, let's put this. Again, I'm just making a set of dummy data. This I'm just talking here, but yeah, I'm not showing you this. I know. I'll show this to you once I have all the dummy data. Let's say that. Uh, okay, let's say that that's K. I have put a value in K in my spreadsheet. And now I'm going to calculate this equal that of this times this times that. Okay. Times that times that. Then plus this times this. Okay, fixed. Okay, I think I may have. Uh, let's make that key really small. Hmm. Hmm. Mm-hmm. Okay. Like I said, fake data anyway. So let's gonna say 0.01. Okay. All right. Uh, okay. Fake data. Let's see how much the temperatures are. All right. This, like I said, it won't make sense, but again, it doesn't really matter in the long run because that's the point of data analysis. You're supposed to analyze data, not comment on the data, right? So, okay, here it is. Okay, I'm not gonna do that. I'll remove that. Okay. Okay, I'll just copy that data here. Paste it as an image, and here we go. So here is the data we're gonna work with. Okay, there we go. So that's the data we're gonna work with. You can see that we got silly values for the temperature, but again, in data analysis, we don't really care about that. Let's use the values as they are. Okay. Now, if you graph this, I'm going to graph this right away in my spreadsheet. And where's the insert graph here? I think it's here. All right. Graph. Where is my favorite graph? Let's use this. Okay. And now I'm going to, you know what? I'm going to change these values. Okay. So I'll do that again. I'll change these values a bit. So that's going to be that. That's going to be, it's going to be this. That's going to be 790. It's going to be 920. It's going to be 1045 and 1180. All right. So, can we refresh? Okay. I think that's still good. So, again, we'll just copy and paste this. Okay. So, hopefully this is good enough. So, let's say that that's your set of data and this is already the process data, not the raw data. Normally in these papers, you're given the process data. If you're given the raw data, just calculate it yourself. I think at this point, you should be familiar with doing that. Okay. So let's say that that's the process data. Let's put the units in. This will be hertz. And then this will be, did I use degree Celsius? Yeah, I used degree Celsius here. Okay. Actually, no, I should not use degree Celsius. I'll use Kelvin here. Okay. So the graph is also given here. And for this graph, I'm going to just improve this for the sake of our example again. So here we go. That's our graph. And you can see that's more or less linear. Okay. And now I'm just gonna add a line. Where's my line here? Okay. Okay. You can probably see that this line is not exactly a line. Not yet, anyway. It kind of curves. Again, if you look at this really carefully, you can see that this kind of curves. So if I'm gonna draw that first, that curvy line, you see, if I draw, oops, should be that. Okay, okay. So there, it kind of curves, right? If you draw that properly. So for now, I'm going to draw a straight line through that, just for now. A straight line is gonna be something like this. Something like that, right? Okay, so if that's our straight line, you can see that we do have some uncertainties. Now, in certain cases, you will draw these uncertainties by doing that. Okay, our uncertainty here would be here to here, and you do it on the other side as well. Okay, so that would be your uncertainties if this were a straight line. Okay, but we know from the equation that this shouldn't be a straight line. It should be some sort of curve. So let's just assume for now that that's the graph, and that's how you do the uncertainties. Okay. However, what I'm gonna do here is I'm gonna add some details. I'll do it here as well. Hold on. It's gonna be f cubed and t squared. Ooh, okay. I think I forgot something. No, I didn't. Okay, so good. So that's gonna be t squared. Okay. So the idea here, one thing you can do is what we call linearizing the graph. Okay. Times. Hold on. I'll just do this real quick. Times. Okay. Right. So that's the first one, and that's gonna be this squared. Right. Times self. Okay. Give me a moment to put these values in here, and I'm also gonna graph this right here. Uh, where's the chart again? Scatter plot. Oops, why did I do that? Undo. Should be this. Insert scatter plot. This is weird. Mm, okay, give me a moment to see what's happening with my graph. Chok, 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 chok. Ta-ta-ra-ra. Hmm. You know what? Okay, let's leave it like that. Okay, so I'm gonna try it one more time just to be sure, safe. Okay, so that, then insert the scatter plot there. Okay, yeah, I'm really getting the same graph. So, okay. So now if we go back to the board here, okay, this is a second graph we would get if we use the equation as our basis. Okay. So you can see here that is actually closer to being a line with the exception of our first few points, right? Now, why does that look like that? Because, let me take a screenshot of this thing. Because what we did here is we linearized the graph. You know, what does linearization mean? Or linearization of the plots? What we did is we actually just followed our equation. Look here. This is what I mean. So we have f here, but in our equation it's f cubed. So all I did was take f cubed. All I did was actually get this, and I did 100 cubed. Similarly, that's going to be, this one's 100 cubed. This one is 150 cubed. This one would be 200 cubed, and so on. So all I did was do that. Similarly, for the temperature, all I did here, according to our equation, we have T squared. So all I did here was, for the first value is 500 squared, and that's the value. Similarly here. Okay. Now, again, as you can see here on the two graphs, this is more or less a curve. This is, let's take a look if it's actually more of a curve or more of a line. Let's put the line thing here, and I'm going to start here. You can see that they are at least, for the last few points, more closer to a line. Compare that to this. Okay, it's just these points that don't look nice, but that's fine. We're gonna analyze that. So the idea here is, once you have these graphs, how do you interpret them? The idea here is that the question will either be, does the data support the hypothesis? Okay, so basically this is our hypothesis, right? Oops, change that out. Okay, so that's our hypothesis, right? And in this case, does this support the hypothesis? Or actually also that, yeah? Support the hypothesis. Okay, the answer is always yes or no. The answer will always be yes or no. However, we have to be careful here. When do you say yes? You say yes if the linearized graph, so let's label this. This is the linearized graph, right? This is the original graph. Okay. The answer of does it support the hypothesis is yes if the line is straight and the y-intercept is as seen on the equation. Okay. Now, in this case, our equation has a t0 squared term there. So in this case, we need a y-intercept. So let's assume first that this is a straight line. In our case, let's assume first, yeah? In this case, this is a straight line and there's a y-intercept. That's our y-intercept for t0 squared. And then we find t0 from there. Okay? That is again, excuse me, assuming that that's a straight line. Now, going back to the other one. When is the answer no? The answer is no if the line is not straight. Okay, here in yes, it has to be end, right? Here in no, it's an or. The y-intercept is incorrect. Is incorrect. Okay. In other words, if it has a y-intercept, or but it says it's 0 on the graph, or the other way around. If your equation says there must not be a y-intercept, but the graph says there is, it's not as seen in equation. Okay. So let's answer this question according to our graph here. Does this support the hypothesis that t squared is a function of f cubed plus some constant here? The answer here is actually, and I'm going to just use which one? I'm going to use pink here. The answer here is no, because points do not, the points are not lining up correctly, are not on the line, right? That's the answer here. So again, right or wrong, you know the equation or not, you know the theory or not, does not matter. You look at the data and you should be fine. And you interpret the data properly, you should be fine. Okay? All right, so that's with graphing and a little bit of uncertainties. Okay, let's work with actual uncertainties now, okay? Because another thing that normally comes up here is sometimes you are given, again, this is for both A level and IB, as I've said. Okay, and that's why I really love this topic in particular, because it doesn't matter what qualification you're doing. Okay, so let's take a look now. Let's say, let's add this text. The data taken for the frequency. Okay, the data taken for the frequency is has a 5% um, uncertainty. Okay. The question is, what is the absolute uncertainty in, let's see, in the temperature of 500 Kelvin? Okay. In the temperature reading of 500, 100 Kelvin. Again, this is a common type of question you would see. Okay. Certainty in the temperature of 100 Kelvin. Okay. 100 Kelvin's not that hot, is it? All right. Why did I pick 100 Kelvin? I don't know. Not 100 Kelvin. 100 temperature would be 500 Kelvin. There we go. That's why it's wrong. 500 Kelvin. Okay, so let's start with that. So, let's take a look at that data first for 500 Kelvin. You see here that the frequency is 100 hertz, right? Okay, so let's start with this. Before we answer this, remember, this part for uncertainties. This is in the data booklet, but I'm gonna mention it anyway. So so basically, let's start with this. We have three possible rules. If A equals B plus C, then, or minus for that matter, then delta A equals delta B plus delta C. Always think absolute. Addition, absolute. Okay, addition, absolute. Okay. Now, the other one, if A equals, let's do a D here, A equals B C over D, then delta A over A equals delta B over B plus delta C over C plus delta D over D. Okay. Now, absolute. Now, how do you memorize this mnemonic? Again, even though this is in the data booklet, this is um, fractionals divide. So fractions, there's a fraction here, right? Fractions means fractional uncertainty. Okay, the third one is a derivation of the second one, but it's worth noting because it's a shortcut. So in this case, the shortcut now is if A equals some number B or some value B raised to some exponent, then delta A over A equals N delta B over B. Specifically, let's put all of that in absolute value. Okay. So you could have a negative exponents. For example, b raised to negative 5. It's still not going to matter. We're still going to use 5 in the whole thing. Okay. All right. So going back here, and how do we solve this? The data taken, let's again, let's put that here. And this is where this is going to be our last topic, or our last thing here. In this particular case, we say that the temperature is 500 Kelvin at the frequency equals 100 hertz, right? It says here that your uncertainty is 5%. So delta F over F is automatically 5%, okay? You don't need to solve for that actual delta F. No need. No need to solve, okay? No need to solve. Okay. If you do have to solve for it, it's fine. Go ahead, solve for it. But in most cases, if you're given this, you don't need to do that. Okay. Why? Because we're looking at this. We know that t cubed, let's put that equation back in. T cubed is equal to k f squared, or the other way, squared here and cubed here, right? Plus t0 squared. Now, in this case, this means it's a combination of addition and multiplication, right? So I'm going to do this first. What's the uncertainty in t squared? I'm just going to do it like that in bracket. What's going to be the uncertainty in k f cubed? Again, the whole thing in bracket, plus the uncertainty in t0 squared. Okay, so that's the first part. Okay, so in other words, let's ignore this for now. For now, ignore. Okay, now negligible. Negligible. Okay. Now you will see here that if we're gonna ignore the delta t0 squared, you can see here that there's some sort of relationship, and then you have the squared. So let's go back to this. So basically, this means I can, what's the uncertainty in t, right? So I'm gonna use this for now, purple. Okay. So once we solve for this, what do we get? This is gonna be uncertainty in t, 2 times the uncertainty in t over t, right? Is equal to uncertainty in t squared all over t squared. Now what happens? We're gonna move stuff around. So from here, we can see that that t and this t cancels out. So the uncertainty in t squared would be equal to, okay, I think I messed this up. Okay, let's do this later because this is gonna be more difficult if you start there. Let's start with the other one here, k f cubed. So let's do the multiplication thing. So, okay, so this is gonna be the uncertainty in k f cubed. You see they're multiplying in here? So that means we're gonna have to do a fractional uncertainty as well. Okay, so that's gonna be equal to the uncertainty in the k over k plus the uncertainty in f, but we're gonna have to put 3 there over f. Okay, now since k is a constant, that's going to be 0. I'll write that here again. The uncertainty in a constant is 0. So that's going to be 0. So in other words, our uncertainty here, so delta t squared, let's put that in here, would be equal to basically the 3 times the uncertainty in f over f. Okay, now let's just substitute now. Our uncertainty here is 5%. So that's going to make us automatically 15%. That whole thing's 5%. So the whole uncertainty in t squared is 15%. Okay. So we are looking for the uncertainty in the temperature at 500 Kelvin. So we're going to use that here. Now remember, did I miss anything? Hold on. I think I may have missed something. Yeah, I missed something. Sorry. I missed something, but it's not big. Okay. So we're gonna put this in, and you see here, um, okay, so that's gonna be the delta kf. So we're gonna look delta kf now, cube. That's gonna be equal to k f cubed times 3 delta f over f. Okay, this f cancels out with this becomes squared, and our k doesn't really matter at this point. We can find that k later. I think I'll just give you the value later to make it easier. I used a value of k equal to 0.1. So we'll use that. Okay, so our value of k is equal to 0.1. Um, we're gonna, oh, sorry, I used c earlier. I changed that to c. So let's change that to c as well. Okay, so delta c over c, delta c, c here, c here, and c here. Okay, so going back. So the idea now is our delta f, our delta cf cubed is actually equal to cf squared 3 times delta f. Actually, that's not even that's even a bad idea because we know that's 3%. So I'm not even going to cancel that f anymore. You see, even if you know what you're doing, you sometimes backtrack and see a better version. So f, right? This is still going to be cf cubed. So we're going to have cf cubed here times our delta f over f is 5%. So that's going to be 5%. Okay, so that's it. So that's the uncertainty in cf cubed, right? So our c is 0.1, 3 times 0.1. Our f cubed, our f was in the problem. Let's go back. Our f temperature 500K, look at the look at the data. That's 100 hertz. So 100 times 100 times 100 is a million. Okay. So going back here, that's going to be 1 million, or 1 times 10 to the 6 times 5 over 100. Okay. So that's one way to do it, but I'm not going to finish it. I'm just going to keep, in fact, I'm just going to keep that right there. Okay. Now, the next thing we're going to do to make this faster, instead of trying to solve for everything all at once, is I'm going to do this next part here. What is delta t squared? So remember that delta t squared is equal to delta of cf cubed. And now we have that. Um, but we know one more thing here. So we know that this is going to be, let's put it here on the side again. So let's use gray. So if we put that on the side, delta t squared over t squared is basically just 2 delta t over t. So in other words, so we've kind of done that earlier, so I'll just rewrite that. So basically our delta t squared is equal to t 2t delta t. That's it. So we can substitute that into here. We have 2t delta t equals delta c. Oh, I forgot the 3. Delta cf cubed first. Now we substitute this in here. So 2t delta t, so the t is here, would be equal to 3cf cubed times 5%. Finally, we solve for delta t. So delta t is equal to 3 halves cf cubed over t times 5%. We now plug in our values. This is 0.01 from given. This is 100 cubed. And our temperature is 500. Find, and you're done. Okay? All right. So with that, again, these are just really common ways that you would see problems across all types of exam qualifications. And I hope you learned something from here. I know for a fact that this last part is the most difficult part, but everything else should easily follow once you know what to do. Okay, so let's summarize everything before we end. So again, where do we start? And the rest of my writing's gone. There we go. Okay. So again, once you're given the equation, don't give into the temptation to find an equation in the data booklet or data sheet or whatever other thing you've been given. Resist that temptation. Start with the equation that's given to you. Okay? Then from the equation given to you, you can either find the value of some constants, in this case CF cubed, we're looking for the C. Once you find that, you're gonna have to deal with uncertainties. Uh, okay, here are some techniques to reduce uncertainties in the experiment, but in terms of the paper, what do you do when dealing with uncertainties? You'll just basically use what's given to you in the data booklet. Again, these things are in the data booklet. I gave you a rather difficult example for an illustration, but that's the always going to be the idea. Easier examples are always in past papers and in exercises given to you by your teachers. Okay. And the last one here is when you're graphing, you must have a straight line either in any of your graphs, whether it's the original graph or the linearized graph. If none of them follow a straight line, or you don't have a y-intercept that matches the equation, then no, you do not have a correct hypothesis. If they match, then you do have a correct hypothesis. Okay. All right. So that's the summary of that. Hopefully you learned something, and or if not, you have reviewed something here. So let's go back now to this. So again, guys, don't forget to like, share, subscribe to the channel. And yeah, yeah. Okay, hold on. My green screen isn't properly aligned. Let's align that, shall we? All right. So there we go. So again, don't forget to like, share, and subscribe to the channel on YouTube, Facebook, Instagram, TikTok, and Twitch as seen on the screen. And with that, everyone, I hope you learned something. So good night, good day, good morning, good evening, good afternoon, wherever you are in the world. And stay freaky, everyone. Bye bye now.